Hello. So, um, one of the graduate courses I'm developing right now, the other is called Applied Nonlinear Dynamics and Control. So the course is based on various courses I took during my master's and PhD. I had during my master's, I had a couple courses. One was multivariable control, and one was dynamical systems theory. And then I took a nonlinear dynamics course and another couple courses during my PhD. So I'm trying to combine all these. So the course, I'll say 40% of the course is going to be nonlinear dynamics, but then 60% is going to be nonlinear control. But it starts with nonlinear dynamics, it just makes sense. The textbook or reference books is more accurate, are going to be these textbooks simply because I studied nonlinear control using this textbook, and then nonlinear dynamics. I used both this nonlinear dynamics textbook and Strogat's nonlinear dynamics as well. So I'm going to start with an introduction to dynamical systems and phase plane analysis, a review of linear systems. It's included there these chapters and sections of these textbooks, and then I'm going through stability, various types of stability analysis and various types of stabilities like asymptotic stability, exponential stability, etc. I'm going through bifurcation, and once I'm here, then I'm switched to mostly nonlinear control and Lyapunov's method again, and then advanced stability theory, chapter 4, and then chapter 5, and feedback linearization, which is chapter 6, and adaptive control robotics is chapter 9 of this textbook. And once I'm here, again, this whole thing is going to take a long time. It's going to be maximum one video lecture per week. And when I have time, some simulations, solved examples, etc. And if I win, I set up a personal website. It's going to be some assignments on the website. So robotics, once I'm here, depending on when I'm there, I might switch to the other textbook that I've read. It's a Sponge, like fundamental robotics book. I think this is how the name is pronounced, and this is Slutin and Lee again. This is, I think, how the names is pronounced, and Naifi and Balachandran. Yes. So now let me just cover some introduction about 5 minutes, and also make the videos as short as possible, because I personally have very short attention span, so I make them very short. All right. So let's see. The introduction is just one short introduction. Yeah, I just hope that everything is inside the frame. All right, so the first question you might ask, and you should ask, is why we study nonlinear dynamics and why we study nonlinear control. Now, nonlinear control is mostly the nonlinearities are introduced into the system artificially. Nonlinear dynamics, again, it might be artificial nonlinearity, or it could be natural nonlinearity. So think about this mass spring system. If you use your one thing is about these are graduate courses, in this course and the other course I'm developing, rigid body dynamics and control. For this course, the prerequisites I forgot to mention are a vibration course and a linear control course. All right. Now, at the end, when I get to robotics chapters, it also requires dynamics. So first course in dynamics is at the end, but at the beginning it's a first course in vibration and a first course in linear control. And then it also requires a first course in dynamics. All right. So why nonlinear dynamics? If you think about your mass spring system, a system like this, and if you write down the equation of motion, you're going to see that equation of motion is mx double dot plus kx is Fe, right? Fe is an external force. All right, so I'm applying this force and I'm writing the equation of motion. So once I write down the equation of motion, I get mx double dot, which indicates the acceleration of this mass, and then kx. Kx is the force caused by the restoring force created by a spring. Now, if the operation range is large, this kx, which is a linear function of displacement, right? Because k is a constant and x was our displacement. This is not enough to describe the restoring force. It turns out that in various cases, we see that the force needs to be proportional to x plus x cubed, and then it becomes a nonlinear force, right? And then once we have that, we actually see some interesting dynamics, meaning that, and then nonlinear dynamics is the dynamics of this nonlinear mechanical system. But when we say nonlinear dynamics, it could be a nonlinear electrical system, right? So that's why nonlinear dynamics is important, because then we need to study the dynamics of the system. We use certain techniques. That's what we're going to talk about. But we're also going to talk about nonlinear control. Again, 40% of the course is probably nonlinear dynamics, or half of the course, and then second half is nonlinear control. So you might say, all right, the operations range is a small, kx is enough. But then I might say that, all right, so my system needs to operate in certain range so that this x remains small. But then Fe is such that my external force, which is a naturally caused force, for example, my force is such that it forces the system outside this small range. So then you might say, all right, so then I need to introduce a nonlinear controller such that I force the system to stay in that small range. And that's the topic of nonlinear control. So in control, we study controllers. And controllers could be linear, as in linear control. For example, a proportional a PD controller, which gives us a signal proportional to displacement and velocity, for example. But it could be a nonlinear function of displacement and velocity. All right. The other thing is nonlinearities can be continuous or discontinuous. So think about it this way: if I had my mass spring system, but then I had some obstacle here, such that once this x was larger than a certain number, this mass was going to hit this wall frequently, and then it becomes a discontinuous force, right? And let's say my wall on its own was connected to a spring, a nonlinear spring on the other side. So it would frequently experience this nonlinear discontinuous force as this mass goes back and forth. All right. Now, in general, what is our end goal? So what is it we are trying to do in this course? or what steps do we need to take to achieve our goal. So if I give you a physical system, a real physical system, a natural physical system, or an engineered physical system, the first thing you need to do is you need to develop the mathematical model of the system. For that, if you have, for example, a mechanical system, mostly it's true for our case, you're going to use, for example, Newton's second law, and using that, you're going to develop your mathematical model. Once you develop your mathematical model, the next question is, what is your desired state? Just back to this example, I said that let's assume that my desired state x needs to be limited between x1 and x2, right? Between 1 millimeters and 2 millimeters, for example, something. And then this is my desired state, but then you would say, all right, does my natural dynamics of the system provide me with that desired result? If it does not, then I'm going to say, all right, can I design a controller to force the system to stay in that range? And if I design that controller, does a linear controller provide me with my desired outcome? And then we move to a nonlinear controller, because the linear controller, for example, does not provide us with the result we're looking for. So we go to nonlinear controller. For example, the performance of nonlinear controller is better. Might be faster. It might stabilize the system faster. So, and it might require less energy, for example, something. So we use nonlinear controller. So this interaction between system and the controller is improved, for example, using a nonlinear controller. And one last thing here is, when we say system, we don't mean just mechanical system or continuous systems. We could talk about discrete systems. Think about this. So let's say this system describes the model of a bank account. It is a dynamic system, and my bank account receives a certain interest at the end of each year. And then this is a simplified model. So after 1 year, k plus 1, my current account, xk, describes my current balance, is going to be is going to receive some interest, and it's going to be 1 plus 0.5% more than my current balance. So my new balance is 5% more. So this is how we describe the system. But then you're going to say, all right, so if I compute the numbers for this dynamic system, I'm going to see that after 10 years, my account is going to have certain balance, but that balance is not my desired balance. So I'm going to introduce a controller, right, UK, and this controller, for example, in this case, is going to be like, all right, so on top of the interest I receive at the end of each year, I need to deposit some money into my account, such that after 10 years, my account have the desired amount that I'm looking for. All right. So when we say dynamic system, the whole point is, when we say dynamic systems, we don't mean just mechanical dynamic systems or continuous dynamic systems or electrical dynamic systems. We mean also discrete dynamic systems. And in fact, they share many things. And the other thing is the importance of discrete systems is that computers are digital. So in many cases, so we need to sample our continuous signal, and then our continuous problem may turn into a discrete problem. So when we say dynamic systems, we talk about both continuous and discrete dynamic systems. All right, so this was just a course. So we had the course again. This is going to be the course mostly, and then 48% or half of the course is than half of the course nonlinear dynamics, and then I moved to nonlinear control. I'm going to use mostly these two textbooks simply because they were my textbooks. I had a multivariable control course based on this textbook, and I had a nonlinear dynamics course based on this textbook. So this is the two textbooks I'm mostly using. All right, thanks for paying attention. Seeing you next time.